Today I'm going to start talking about the vector algebra, right? I won't be able to finish today because that's actually a huge topic. And later in the second year, you are going to take the linear algebra from math department. It's a math 260 course. Probably there will be a little bit more in there. But we are going to see in here that the essentials in here, the essential operations that we are going to use. So let me first of all say this. So this is basically a file in, I think in the first week, it's the vectors for physicists. It's a file that I have written down. So everything that I'm going to talk about vectors is in here, right? Just keep this in mind, okay? So I'm going to repeat more or less the same things in here. There is another thing in here. So some of the operations, some of the mathematical operations that we are going to define doesn't have enough justification, physical justification. So the only thing that I can say in here is that these things are going to be useful at some point later, all right? Unfortunately. So we are going to use the dot product, for example, later when we see the work concept. We are going to use the cross product when we define the angular momentum and the torque concepts, all right? So they are going to be useful later. Here, what I can do is to explain these in a geometrical way. So try to understand it like this. So the whole justification is that it appears that these are useful, okay? So what's the idea in here? So I have talked about quantities before, and I have said that this is one of the features of the quantities in physics. Some quantities are scalar quantities, and some quantities are vector quantities, okay? It appears that there are also other kinds of quantities as well. So there are these tensors as well. There are tensor quantities. But let's just forget about this in here because, well, in this course, we're not going to see any tensor quantities, with a small exception, but I'm not going to mention this anywhere in here. Even in the undergraduate study, in the must courses, you're not going to see any such tensor quantities. So as a result, let's just forget about them, okay? So as a result, you can think of every quantity as a scalar or a vector, right? So the scalars are just numbers. Any quantity that I can specify with a number, with a single number, is just a scalar, right? You can think of it as the real number. The concept of real number in mathematics corresponds to this, but just keep in mind that these quantities have also dimensions and units and whatever. Okay. So vector quantities, however, they have a magnitude as well as a direction. So let's say it like this. I'm just going to say it like this. These are basically quantities with a magnitude and a direction. And a lot of quantities in physics are of that kind. The velocity and acceleration, force, electric and magnetic fields, and things like that. They have a direction, and this direction is important for physics, right? Some directions actually make some important difference. So if the velocity is like that and the acceleration is perpendicular to that, so something else happens in there. So we will talk about some of these. And so the direction information somehow enters into physics formulas directly, right? So the formulas are not about the magnitudes only. They also contain direction. But to be able to handle that direction information inside formulas, we have to define the operations with vectors. So we have to understand what does it mean to multiply a vector with a number, or what does it mean to multiply two vectors, okay? So it appears that this is a little bit complicated. When the direction is at play, for example, I can define the product of multiplication of two vectors in two different ways. And both of these ways make sense in some certain places. So the one product is useful in some certain situations. The other cross product is useful in some other situations, right? So as a result, it appears that these are going to be useful. So this is kind of complicated. So you can think of it as part of mathematics that's called algebra. I don't know the precise definition of this thing actually, but probably, you know, things from like polynomial algebra and things like that. So these are really not numbers. I mean, you're basically manipulating some mathematical symbols, but these symbols may not be numbers. Like in polynomial algebra, you're working with a variable x, for example, right? You just multiply this with each other and things like that, okay? So as a result, I mean, you can think of that corresponding to a number variable, but it is still a symbol in there. In the vector algebra too, we are going to be dealing with some manipulations of addition of vectors and things like that. But I mean, essentially it's like it's like the polynomial algebra. You're just manipulating some symbols. So when we see the examples, you're going to see this better, perhaps. Okay. Unfortunately, a lot of students, I don't know why, think of the name vector as some kind of a title, some sort of a title. Like title is something like this, right? It's like Professor Dr. Ali, for example, Ali Bedi, I don't know, Ali Yilmaz, right? So this is the name of the person. You can just call him as Ali without a title, or you can express it with the title, right? You say it's Professor Dr. Ali Yilmaz. So some people think that, well, being a vector is like a title. So as a result, out of respect to these quantities, we have to say that they are vectors. No, it is not, right? Mathematically, they are different quantities. I would like you to think of them as like, for example, just like a triangle is different from a number. A triangle is some kind of a mathematical concept. So as a result, you cannot treat this as a number, right? So you can also say that, for example, this triangle is different than from, for example, this triangle, right? Because geometrically it's a different shape, okay? So a vector is essentially, right, is a directed arrow in, let me say, 3D space. You can also define vectors in some hypothetical spaces as well, but that's something else. You're going to see this kind of approach in linear algebra courses. But in this course, whenever we say a vector, we're talking about this particular space, and it's just an arrow in that space. So this arrow has a length. So the length is the magnitude. So that's the magnitude. And there's also this direction of that arrow, right? Think of it like this. It's just a geometrical thing, right? Just like a triangle is a geometrical object, this arrow is also a geometrical object, but we are going to treat this mathematically. So what is not intuitional is that on these directional arrows, we are going to define some mathematical operations. So I'm going to multiply this geometrical shape with a number and say that this is another directional arrow, right? So we are going to define mathematical operations like that. So probably you haven't done anything with triangles, any operations like that, because nobody has actually found the necessity of defining such operations. But for these directed arrows, we are going to define them, right? So think of it like that. So a vector is an arrow in space. It can be longer or shorter. So the length is an important property of the vector. The magnitude is just a scalar, but it's a quantity, so therefore it can have a dimension. So if it's a velocity, then it has a unit, right? Whatever, so just keep this in mind. But here, I'll be talking about, for simplicity, I'll be talking about with dimensionless vectors, right? Just keep this in mind. So by this, I actually mean that. So if I have a vector in here, this vector is different from that vector. Okay. Sorry. This is a straight line, right? Even if their lengths are the same, they are different, right? And of course, if the direction is opposite, so it's not the orientation, it's not the orientation, it's the direction. So therefore, this vector is also different from the vector in the opposite direction, even if their magnitudes are the same. So just keep this in mind. So we will be basically saying that two vectors are the same if they have the same magnitude and same direction. So the starting points do not matter. Okay. Starting points do not matter. Let me say it like this. Yeah, let me not write this thing down in here. Or let me write, sorry. Two vectors are equal as the mathematical equality if they have same magnitude and same direction. Okay. So that's the vector equality. So, some people think that the starting point of vectors are also important. So they may call two vectors that start at different points as different vectors, but that's nonsense, all right? We don't define vectors like that, okay? So the starting point is irrelevant. So I can perhaps, I can shift the starting point of the vector. I still have the same vector, right? So our notation for the vectors is this. It is this notation here, okay? So symbolically, I'm going to use it like that in my notes and also in the homeworks and the questions and things like that. I just put a vector sign on top of the symbol. I'm not putting this sign out of respect. I mean, it's not a title, okay? I'm specifying that this is basically a different mathematical object, okay? So as a result, if I say anything like that, for example, if I say that, well, this is equal to, for example, 5 meters per second, then this is nonsense, right? That's basically, I would treat this as a nonsense because this is a geometrical object, but that's a number. So this is a stupid thing because you cannot say, for example, a triangle is equal to 5. So as a result, if you cannot say this, you cannot also say the same thing for the vectors as well. So geometrically, a vector is a different thing than a number. Vectors do not have starting point as a property, but some vectors like force vector, they have a special property called the application point. So, okay, right? But they don't start at that point, right? A force is just a force vector. But the force concept has an application point, right? Probably because of that reason, some people confuse this. Okay. So, I mean, two vectors can be equal even if they start from different points. That's what I'm trying to say, okay? So in any case, that's nonsense. So don't do these kind of things because I'll get offended, right? So the second thing, lots of different things in here. So I'm going to use this notation to express the magnitude of a vector, right? Vector A, right? Magnitude. This is always a positive number or zero. right? 0 or positive. This cannot be negative. We use the absolute value sign, but sometimes people use this. I mean, later mathematicians actually use this double absolute value sign, but I'm just going to use the absolute value sign, right? So as a result, this is meaningful. So for example, the magnitude of the velocity vector, that's 5 meters per second. So that's okay. Okay. So basically, the magnitude is a scalar. It's just a number, but this scalar has to be always positive. I mean, can never be negative. Okay. But it's a scalar because it's just a number. So in any case, we have some definitions. Zero vector, right? Zero vector is basically any vector that has magnitude 0, right? If the length of the vector is 0, we just call this as a zero vector. And then in that case, we show this vector by this sign in here, right? It's just an arrow on top of 0. However, I mean, that's not that important. So we don't, I mean, strictly speaking, we have to put a vector sign on top, but people do not make mistakes because they missed this sign in here. So as a result, I'm just going to be sloppy and then show this by a single 0 number as well. But I'm not claiming that the 0 vector is equal to the number 0. They are not. It is not, right? Because numbers and vectors, these are different things. But I don't want to spend too much time on putting an arrow sign on top of 0. So as a result, I'm just going to use this symbol in there. So I'm just going to be sloppy. So that's actually a bad notation, but let's just forget about it because nobody makes mistakes because we forget an arrow sign on top of 0.
So may I ask something?
Yes.
What application does the zero vector have?
Does it have? No, it's just a vector, one of the possible vectors. So in equations, of course, we can have 0 vectors appearing somewhere. Okay, I mean, it is possible that the sum of 2 vectors is equal to 0, for example. In that case,
no specific applications.
No.
Okay.
Yeah. So does the 0 vector have a direction? Direction is meaningless. So as a result, I mean, you cannot have different 0 vectors because they have different directions. So that's nonsense, right? So let me say it like this: the direction for 0 vector is meaningless. Right? Let's just say it like this. Or you can say that any direction is a possible direction for a 0 vector, if you want. There was another question. Somebody said.
No, I was going to ask about the direction, but you said already.
Yeah. So, I mean, at the end, you're going to justify this when you start doing the calculations, right? So when we define the direction in a certain way. So for 0 vectors, we cannot define the direction. Okay. And then we have the unit vectors. Unit vectors are the unit vectors where the magnitude is equal to 1. Again, this is dimensionless. Basically, the vector itself is dimensionless in that case, essentially, because 1 is dimensionless, right? Unit vector is dimensionless. So we use a special notation, special hat notation for unit vectors. So instead of putting an arrow on top of them, we use a hat on top of them. Okay. So as a result, whenever you see a symbol with a hat, you understand that it's a vector, but it's also a unit vector, right? So when I say, like, without saying and hat at some point, so you will understand that, right? this is a unit vector along some direction. Let me write completely. Why do we use unit vectors? Well, basically to actually specify a direction in a mathematical way. Right? Instead of saying towards north, I can say a unit vector along the northward direction and just call this as like n hat, whatever. So we have the coordinate unit vectors. I think I'm going to talk about the coordinate frame later. At some point, I'm going to talk about them, but in any case, you don't have to define a coordinate to be able to define vectors, all right? So the coordinate, a coordinate frame is needed for some certain purpose, but I mean, to be able to talk about the vectors, we don't need a coordinate frame, right? But to be able to use what we call as unit vector notation. So I'm going to talk about this later. I mean, there is an algebraic way of expressing a vector. To be able to use such kind of a notation, we need a coordinate frame. But apart from that, to be able to define a vector, I don't need a coordinate frame. But in any case, if you have a coordinate frame, then there is a unit vector that I can use for expressing the direction along the x direction. So I'm going to call this as I. The unit vector along the j direction, y direction is called j. And the unit vector along the z direction is called k. Right? This is the ijk notation. Right, so that's the ijk, and when I'm writing, of course, I don't show the dots of I and j. That's the convention. So as a result, some people can get confused by this. A lot of people actually use the x hat, y hat, and z hat notation. You can also use this one, no problem with this. Everybody will understand these. So that's the unit vector along plus x direction. Okay, so we have just a special name for the unit vectors along these three special directions. Okay, I mean, whenever we have a coordinate frame, a reference frame defined, people use these names for these three special directions. Okay. Whatever, so I can also do the same thing for these other ones. Let me just add in here, sometimes later you are going to see that some people use some other notations for these directions. So in physics, sometimes we would like to use numbers as, I mean, sometimes we would like to label the coordinates as x1, x2, and x3, for example. In that case, we find it useful to show the unit vectors like that. Some people use this EX, yeah, whatever. I mean, there might be different notations, okay? But as I said, in this course, I'm going to use this notation, especially in homeworks too. And when you are coding some vector expression inside on online homeworks, you also are going to need to use these notations as well. Okay, just keep this in mind. So let me also draw this again.
So what about the negative direction?
Negative direction. So I'll just, yeah, I'll be basically talking about this, but I need one operation in here. It's the multiplication of a vector with a number. Okay, so once I define that operation, I can answer that question. So
okay.
Basically, any other vector can be expressed in terms of these three vectors, three unit vectors, and that's why these are important. Yes?
Jim,
Yeah.
horizontal unit vector is an I or an L?
It's an ijk.
Okay.
Yeah, the three letters that follows each other, right? ijk. EJK, if from the French school, of course, some people call it as call them as EJK. But yeah. But since we are speaking English, I'm saying IJK. Okay, so in any case, so we define some operations with vectors. Okay, so these are operations that I can do with the vector concept, right? So you actually know these operations. I mean, these are kind of natural. So as a result, you can easily accept them. And some of them you already know. So as a result, I'm just going to quickly get over with these. So the first one is this multiplication of a vector with a scalar. Whenever I say a scalar, this is just a number, right? A vector is vector, basically. So let's just take this example. I'm going to take this A example. So that's my vector A. So the question is like, I have vector A. What do I get if I multiply this with 2 times? With 2, for example, what is this? And the natural way to answer is that, well, 2A would be then a vector, which is twice as long as the vector A, and it's in the same direction. Did I draw the direction correctly? Yeah, whatever. I mean, when I'm drawing things, perhaps my hand is shifted a little bit upward or downward, so they are not perfect shapes. They cannot be. I'm an imperfect human. So as a result, I mean, just think of these as symbolic expressions, all right? Symbolic drawings. So if I multiply this with 3, then I'm going to get 3 times longer vector in the same direction. Well, I can continue like that, all right? So the magnitude is basically increases by the number that you multiply. In the same way, 0 times A is basically the 0 vector, because the length becomes, the magnitude of the vector becomes 0. And so as a result, you can guess that if I multiply the vector with a negative number, so it's -1 multiplied with A, then I get, do I get the length correctly? All right, let me just draw this a little bit longer. So in that case, -1 times A has the same magnitude as the vector A, but it is in the opposite direction. And similarly, we can continue like that, okay? So it is -2 times A is like that, right? In all of these, of course, I'm going to use the shortened notation. So instead of -1 times A, I'm just going to write -A. We actually do this with the symbols, right? Instead of -1 times X, for example, in polynomial algebra, we do this, right? -1 times X is -X, okay? So in any case, we are also going to do the same thing for the vector algebra as well. So we have these kind of notations. Can 0 vector be counted as a point in 3D space? So yeah, it's a point. I mean, but it's a point as a geometrical object. And it doesn't matter where the point is, obviously. So still, I'm thinking of it as a directed arrow, but the arrow has length 0. Okay, so as a result, this is basically meaningful. And so therefore, the -1 times A being different than A is also meaningful. So we get a meaningful definition in here. So as a result, well, this is just a multiplication of a vector with a scalar. Okay. So why do I define it like this? Well, it seems natural, but I cannot justify it right at that point, right? It's not possible to justify. The only thing that I can say is the thing that I'm going to repeat. Well, at some point, we are going to see that, well, these operations are useful, right? So that's the first example. Why do I define it like this? Well, at some point, it will be useful. Because I cannot provide any justification because we haven't actually seen any use of the vectors yet. But at some point, I'm just going to solve some geometrical problems by using vectors. Okay, so let me not write down any definition in here. Everybody can understand what we are doing in here. Okay, so the second thing is addition of two vectors. Okay, so we have presumably a vector A and another vector B. And then by using these, I would like to define a vector that I can call as A plus B. Okay, how do I define this? Well, it is basically something that you already know again, because I know that you have done these kind of things in high school. So A is a vector like that. And let me just do this like this, right? So B is a vector like this. How do I define the geometrical addition? So what I do is I just shift one of the vectors so that the starting point of one of the vectors is equal to the ending point of the other vector. So let me say it like this. I'm saying that arrange the vectors tip to toe. Tip to toe. So that means the tip of one of the vectors is the toe of the other vector, right? You can think of it like this. This is the tip and this is the toe. So as a result, what I do is I shift this vector B so that it starts at the place where A is ending. Okay. And then I draw, let me use a blue color, the vector starting from the toe of the first vector and ending up at the tip of the last vector. Okay. So you can actually think of it like this. This is the toe part and that's the tip part. And these are the toes and the tips that are on top of each other. You can also think of it like that, right? So as a result, for these vectors, A is this vector, B is that vector. So therefore, I'm going to use the blue color. Yeah. Right, the A plus B is that vector. Okay. So what is interesting in here is that if I do the arrangement, tip to toe arrangement like that, if I started with B, if I started with B and if I started A at the tip of B, then I would get the same vector again. So if this is A, because this A plus B would then be the diagonal of a parallelogram in that case. So that essentially means that the A plus B, I mean, symbolically speaking, A plus B is the same thing as B plus A. Okay, so mathematicians actually give very high importance to these kind of relationships because they actually give some important information about the algebra of vectors. So we're talking about a vector algebra in here. We're defining some mathematical operations with the vectors, right? We are treating these vectors as some kind of symbols. We are manipulating these symbols. And these are the important relationships. So this basically says that the, let me say, vector addition is commutative. The order that you add them up is unimportant. Okay, so I'm going to continue for a little bit, 5 more minutes, let's say, right? So, because I want to finish this addition in here. So that means, so the nice thing in here is that, so therefore, if I have like this other thing, right? So sorry about this. So let's say that I have these 3 vectors now. So A is like that. B is that vector. And let's say that I have another vector C. Then I can define the addition of these 3 vectors, A plus B plus C. How can I do this? Well, I just want to arrange them. I just need to arrange them in the tip-to-toe manner. So A is this vector, B is this vector, and C is that vector. So is it longer? All right. So C is that vector, which means, let me use this color now. So let me raise this. I'll just draw this. Yeah, I think I'm going to use a green color now. It is hard to draw straight lines with these. So therefore, this is A plus B plus C. That's A. Okay, I can also talk about the same kind of a thing. For example, does A plus B plus C is the same thing as A plus B plus C? What I'm saying is meaningless, but let me say it like this. So if I first added up A and B together, and then with the result, I added up the vector C, would the result be the same if I first added up B and C, and then added A? And
Yes.
the answer, and the, yeah. Comment? Yes, and the answer is obviously yes, because B plus C, to obtain B plus C, I need to draw this. So that's B plus C. And in that case, A plus B plus C would be this green vector, okay? And what else? On this side, if I add A plus B, if I get A plus B is this vector. That's A plus B. And if I add to that C, then I would get the green vector again. So the answer is yes. So let me undo all of this because this is kind of complicated. All right. So as a result, it doesn't matter in which order you start adding them up. So we say that, mathematicians say this. So they say that the vector addition is associative. The order is not important. The order that you have done started the summation is not important. The sum of 2 vectors of same magnitude but opposite direction is 0. Yes, that's correct. So as a result, also A plus B plus C is the same thing as, for example, B plus A plus C, for example. The order, you can start the order in any way you want. So therefore, you can start with B. Let me use a different color in here, pink color, for example. Start with B first, then draw C, and then draw A, right? You would get the same thing, right? So as a result, you can change the order in any way you want. And well, I mean, I suggest that you just look at this justification of this thing geometrically yourself. Convince yourself that you're going to get the same thing, okay? So we are going to take the product of two vectors later. So in that case, we have to be a little bit careful. So, I mean, there's still time for this. So let me take a break in here. In the second hour, I'm going to talk about the unit vector notation. So the unit vectors that we have defined for the coordinate for the reference frame, right? For the reference frame, that becomes useful now, because by using those unit vectors and these two vector operations, I can express any vector, okay, as an algebraic expression. Okay, so let me stop here. Stop